So for various reasons, I decided to try measuring a DC voltage with the AC voltage setting on my multimeter. You don't really think of a DC voltage as volatile. It can change and you can monitor changes, but it doesn't really wiggle the way AC does at 50 to 60 times a second. And you don't really think of something complex like an audio signal going to your speakers as a DC voltage. You think of it as a signal. In fact, when you look at amplifiers, it's represented as the AC power symbol. But right now, I'm in the middle of creating a crossover, a DC-based AC generator that doesn't have any magnetic fields intervening. And so I thought the AC measurement might come in handy, so I decided to test it. And I discovered there is some trickery afoot. So let's say I have my messy table and on it my power supply, currently set to 12 volts. So let's just connect these 12 volts through a 1 kilo ohm resistor and back over. So 12 volts divided by 1000 ohms should be 12 milliamps. And if I plug it into the correct hole, that's what we get. So let's go ahead and measure our DC voltage. So I'll set it on the 20 volt setting. I'll measure across the resistor, and unsurprisingly, we get 12. But now, just measuring across the resistor, not changing anything, let's switch over to the AC voltage. Now, here's the fun part. The DC voltage has settings for 200 millivolts, 2000 millivolts, so 2 volts, 20 volts, 200 volts, and 600 volts, right? Lots of different options. The AC voltage starts at 200 and the other is 600. So clearly, this is not intended to be used for smaller bits of AC. And to be fair, you generally don't find smaller bits of AC. AC is wall power, so this is meant for measuring wall power. Well, we're on 12 volts. Let's set it to 200. It'll be less accurate, but it'll still be the right units. Except it's 25.6, 25.5, 25.6. Now, someone who's not using their brain will immediately go, well, clearly this is intended for wall power, it's just not working right with DC. But why shouldn't it? So let's say you have your standard plot of time and voltage. Here's your DC signal, and it can vary. You can have your DC signal go around and around, but in order to measure DC, you just say, oh, what is it? There it is. There might be 2, there might be 3, there might be 4. You just pick a point, measure it, you got your DC. But AC, of course, does this. So let's say you have a DC power supply. You say, I have a 9 volt DC power supply, and it's going to do this. And of course, there'll be noise, but it's going to do that. But if you say, I have a 120 volt AC power supply, where do you measure it to find that out? You measure it here? Well, you better have good timing. So what happens is you take the values over a period of time and you do math on them. You do something called root mean square. Root mean square. Why do we do this? Well, because we have positive and negative. And almost completely, almost perfectly, these cancel. If you add these to these, to these, to these, you'll get roughly 0. That's not useful. So why not just take the average of the absolute values of the samples? You could, but as it turns out, root mean square just so happens to give you a very accurate picture of what's actually going on. It gives you, for physical reasons and statistical reasons, a number that works. When we say 120 volt AC, here's your AC, and if this is 0, then 120, positive 120 will be there-ish, negative 120 will be about there, and the peaks go much higher and lower. Another reason why it said 200 volts AC on my meter for measuring 120. Root mean square kind of gives you a number that represents the waveform that's lower than its peaks and higher than 0, and always positive. So if you took the average of absolute values of samples, you would get a number that's useful, just less useful. What is root mean square? So let's say you just sample the voltage and you say, okay, right now it's that, square it. So that gets rid of the negative sign, plus 2. So you just take a sample and square it, a sample, square it, all the way up to n, which is however many, and then add them together. Divide all that by n. That's a mean, except it's a mean of squares instead of just adding them. And then square root. And for reasons, the squaring actually makes this much more useful. So if you took all those samples of AC that were over 120, under negative 120, and so forth, and did this, you'll get roughly 120. But what if you have DC? I'm measuring 12 volts. Well, 12 squared plus 12 squared plus 12 squared plus plus 12 squared, right? They're all 12. Well, that's n times 12 squared, right? We're just adding it to itself that many times. But then we divide by n. Well, that's gone. And then we take the square root. Well, that's gone. So if you measure DC voltage with an AC meter that uses root mean square to calculate what's going on, you're going to get the right answer. So why didn't we? There are several clues that will lead us to the answer we seek. The first clue is to think about this meter. It's got resistance settings. That works by applying a DC voltage. The meter applies the voltage and measures the current. It's got the diode test mode and continuity mode, which is again applying a DC voltage. It's got a battery checker. Those are DC devices. It's got a high amperage, but that's DC. It's got low amperages, and again, all the amperages are DC, and then all the DC voltages. The only thing on this entire meter that's AC is these two little AC voltages that are perfectly sized to measure wall power here and across the pond. 120, 220, a little bit more. That's the only thing that's AC on the whole meter. And while this was not a cheap meter, it was also not top of the line. So our first clue is there a way to use a DC meter to measure AC and just report it as if it was AC? Do you remember how we turn AC into DC? Step one is you take a diode and you block the negative parts. It wastes half your power, but it's all positive and zero, isn't it? Well, then, of course, you use a full bridge rectifier to put the negatives on the positives and smooth it out and so forth, but wait, it's just measuring. An AC signal is regular. It's a sinusoidal. And recall how these numbers are set just so it's clearly intended for wall power, which is going to be a nice sinusoidal. So if you block half of that sinusoidal, well, you know what you blocked. As long as you measure half, you know what the other half was. 25.5, 25.6. Is that roughly double 12? Double 12 is 24. But it's not, you say. Not so fast. What does a diode have? It has a voltage drop, doesn't it? Well, 25.5 minus 24 that we expect is about 1.5. What is half of that? If we're doubling the 12, what's half of that? Well, half of 1.5 is roughly 0.75. Well, it is 0.75. I'm saying it's roughly measuring that. What does 0.75 sound like to you? Well, a lot of diodes have a forward voltage drop, just regular diodes, around 0.6 to 0.7 volts. Isn't that interesting? So what if this thing is using a diode? When the power is going on the positive side, the diode is forward biased, and it reads voltage minus the voltage drop of the diode. Because it's got a diode, and then it would have a high impedance resistor, a super high impedance resistor. That's how the voltage setting would work, and it's measuring across the resistor. But the diode is going to drop its forward voltage drop. But they know what diode they put in here. They already know what its forward voltage drop is, don't they? So what if they take whatever reading they get, and then they add the known forward voltage drop and treat that as the actual reading when the diode is forward biased? Now, without opening this thing up or looking at schematics or something from the US Patent Office, I'm not going to know that's how it's done. But it's pretty doggone likely, isn't it? Now, what information did I gain from doing this? Nothing. I mean, if I ever need to use the AC setting to measure DC, I know roughly how to adjust it to make it work, but I doubt I'll ever have a reason to do that. I already know that this is going to be too much of a pain in the butt to use the way I wanted to use it, so I'll probably just have to use my oscilloscope program with one of its group modes. So really, this was a dead end. But it's interesting. Get yourself in the habit of thinking. When something weird happens, just stop. Whatever you're doing, it can wait. As long as you're not an ambulance driver, it can wait. Don't just say, oh, it didn't work. Think about why. And you get in this pattern of thought, of being able to just quickly mentally disassemble something, where your very first thought, right after it didn't work, so your very second thought is, well, what do these numbers look like? What does it look like it's happening here? A casual habit of thought and analysis will do you well in all of life, not just this. So I was just amused at that little bit of trickery and decided to share it with you. I thought it was cute. My multimeter is technically lying to me. It's reporting to me things it did not measure. It is not measuring the negative side of the waveform. It is not measuring the voltage when it's below the forward voltage drop of its diode, despite being positive. You know, for all I know, it might say this in the manual, that these are only useful for measuring AC wall power and nothing else. For the record, I do read manuals, and then I forget them. But at least I do read them. But in any case, I suppose I didn't give you any useful information here, just kind of showed you why it's great to be such an analytical person. I hope I'm rubbing rubbing that off on you. It might not have been useful this time, but it might be useful next time when you're dealing with the mass media political propaganda or some dude at work who thinks he's got a brilliant idea and he wants you to invest. There's plenty of room in life for passion, but you should be analytical first. And while you're doing that, I'll be seeing you.